Okay, hello everyone. I am Shiv Prakash, Research Scholar, Department of Electrical Engineering, IIT BHU. Let's start the session for today. This is the NPPT algorithm. Today's topic is how to track the maximum power point take for any PV panel. If you install the PV panel, then you want to take a maximum power from them because of there is no input which one you give there. There is just sunlight and you take a maximum power from them. Then you need a algorithm or a controller to take the maximum power because of you can't be handled by manually all of the thing. That's why there is need of a controller which one track the maximum power. Then this is the important thing how you can take and track the maximum power. Then there is need of any converter. Because if there is a DC, then you can say this is the DC converter. Then you can connect the load or you can connect the grid also. Yeah, or not you can say here from here this is or input, or you can say this one is same as the RT, the terminal resistance of the solar panel, internal resistance for the maximum power. You know about this is the work like a source, and this is the load. No, there is a different thing. Here you can want to take a maximum power. Someone ask like a grid, it is operating at a high power or high frequency. Is a different thing. We want to take a maximum power from a solar. If you want to take a maximum power from a solar, then you need a maximum power algorithm. How you track them. After that, there is some converter, there is inverter to invert the DC voltage to AC voltage. Then after you can connect to the grid. There is a long process. Uh, Inverter, you should take a inverter as a high efficiency, also high power. Suppose if you have like a high power high efficiency works same thing. You think about that. Suppose a room is 10 by 10 feet and 10 feet. Then if you want to make a converter, inverter for high power, then what should the efficiency of them? Suppose there is a large megawatt, like 100 megawatt power. You want to build a inverter for 100 megawatt. Then what should you want to take efficiency of them? Normally you know about the converter, a practical converter efficiency is approximately 90%, 90 to 95% also. But in this case, if you take a 90% efficiency, then what is 10 megawatt is losses of 10 megawatt is a huge supply. This can be deliver the whole village power. I think it is not 10 megawatt of whole village power. I think some town is included here. That's why here the efficiency is more important. in grid system you do they, if you want to take an inverter to make a converter, then they are approximately 99% efficiency you want to take this one. In practical cases here this is a efficiency 98% or 99% efficient converter is used in grid system, because there is a huge power. You can't be loss of 10 megawatt of 100 megawatt power. 10 megawatt is huge losses. Then if you want for the high power system in grid a power system, then there is a very efficient need of control. But here is the sun, and power is coming from the sun. There is no input is there. That's why you want to take a maximum power from them. There is no need of efficiency of converter of solar. Converter is important, but not a solar efficiency. Why? You know about the efficiency of solar, like maximum panel of 16% only from insulation to output. But you want to take a maximum power from them. Then you should design a controller like that. Like take a voltage of this one Vt and current, sense the current, make a power. This was the tracking by a controller. You use a controller to take the maximum power. After that, then controller generate a duty cycle to given to this one. For a Pmax duty cycle, D at Pmax. There is a different type of converter, buck converter, boost converter, buck boost converter, where this is used. Same phenomena, take a current and voltage, then you omit the power of this, calculate the power. After it will taking the with a previously power and this power, P old and P new. This is the delta P. Same thing, you can take a V old and you can reverse of this one also. You can say this is the P new and P old, then V new, then V old. Look at delta P and delta V according to this one. You can calculate all of thing and use the all of algorithm between them also. Because of the control is included in power, and you know the power curve like that. Here you want to track this power. This is a voltage line. This is a current or power line. According to the voltage and power, you can track the maximum power from using a different controller or different algorithm. Okay, but at the old time where the not a controller, not a digital system like discrete system, a microcontroller, there is used as some basic method to find the maximum power. But nowadays all of the algorithm based on the coding only. You can direct code in microcontroller from given only to supply power and voltage current also. From taking these two, you can generate a duty cycle, and this duty cycle given to the controller. Controller adjust the maximum power. I think many are doing in the simulation also, or the buck converter, a boost converter, a buck boost converter, same thing. You can generate a duty cycle like that, which take maximum power from the solar. But the basic of this one, In an analog system, you can say this is a digital system. A microcontroller is used. Digital, you can tightly put a value and give the algorithm, and it will track the maximum power. But in analog system, there is a in the basic there is a mini system. And first one is like sorry, a differential method, which one take a voltage and or current. Yeah, someone want to ask something? Satish Kumar, please write your comment. Second one is the voltage sampling method. Then third one is a power loop method. The hill climbing. This is the basic to track a maximum power. Reference voltage scaling, it means you use the uh, PV panel, which one is same as the voltage output voltage rating, a smaller one, not that one. Like if you take a solar PV, yeah, these things are all of the algorithm based, basic. If you take this a solar system, a high power rating, then you can use a okay, okay. I explain you for the boost converter algorithm how to make a algorithm based. I will give you in the last how you track a maximum power. You can apply in your Simulink. Then you use a sample of same thing like lower power, but actual same as the VOC output voltage are the same, but power is not the same. A smaller one module and take this was a VOC open circuit module. But this is the very common formula like you take a maximum power, maximum voltage, sorry, voltage at a maximum power and open circuit voltage, the ratio of this one like something K. Then you can use a PI controller to track this one only. But this is the fix. This is not as you cannot be change the maximum power voltage because of the this is the fix voltages. You can take only a VOC, but sometime VM have a different because of the shadow and another thing. Then you can't be track exactly of this. But same thing we take a like a VOC and multiplication of K. This will be the VM. Then we'll take VT. VT is a some this voltage, terminal voltage of PV panel. It should be equal to the maximum power voltages. Then it take a maximum power from there. But this is also depending on the or current rating. If the current is very high, then how you can take the maximum power? Because of in your module, a PV module, there's a single current rating where you take the maximum power, and single voltage rating. This is a single current rating. But if you increase the voltage, current, load will increases, the voltage will reduce. Then how you track the maximum power? This is the drawback of this one system. But in previously it was used common basic modulo. Same thing, if you PI controller given some analog value like that with tracking the system, but and then you use the reference to make a PWM like that. This will be the on off time period given, where is on off. This the duty cycle directly given to the into the converter, and converter will track the maximum power. Because of the PI controller, you used to reduce the error of this one, VM and VT, to give a VT as a VM. Same thing in the current controller. Same thing, there is a open circuit. You use same module given as a short circuit of this one and measure the current of this one. ISC. A multiplication of gain, it will be a IM, and track the IM of this one and give this one from the error IT. Use the PI controller, same thing, simply
Hello.
error. Yes, yes.
Sir, I have a doubt in the previous diagram.
Yeah, yeah.
Sir, here na,
Hmm.
that VOC is
Hmm.
getting multiplying factor is K,
हाँ
and then it is becoming VM,
हाँ
and this VM is for the reference cell, na sir?
हाँ हाँ. This is the
And
VM.
this VT is for the panel, no?
Yes, yes.
So, sir, these two will not be the same, no? That
This is
scaling
not.
will be different, na?
They're different. That's why it is taken as a like a VOC of same VOC, but power rating is reduced.
So, sir, every time that if we have this voltage reference method,
हाँ.
then VOC for both will be same or they will be different.
That is a problem of the conventional method like that. These are the fixed value of VM. To given the fixed value of
So
VOC. That's
always
why always the
irrespective of,
same. This is always the same VOC. It will not changes when the load is changes. Some other parameters also changes. Shadow is there, then you can't be find
so sir,
from this one.
if the peak power is different for both, like reference as well as solar PV, but
Yes.
VOC is going to be the same.
VOC is same because of same voltage is taken, and V mic VM will be same for the both at at a particular time. That's why we taken as same parameter of panel, but there is a lower power of the that panel.
Okay, so same VOC.
VOC and VM is same, but
Oh,
lower power it will take
okay,
it.
okay. And it will be always, na?
Yeah.
Okay, okay.
But there is
Thank
a
you.
external errors is not mentioning here, like load is changes and shadow is there.
Mhm.
This is the
Mhm.
conventional method to how to track maximum power from this.
Okay,
Hmm.
okay. Thank you.
Okay, welcome. But in practical cases like modern time, today is very conventional method is occur, like in algorithm based. You should track every time maximum power calculated and taken where is the maximum power. Same thing is for the here. And if you talk about the others, power slope meter, remove this one. Power slope, it means to track a power of this one. It will be a conventional method, but same thing how you sense the voltages. That is important thing, how to sense the voltage. That's one, that one. Maybe. That's why I need our sampling method is there. We can take a voltage sampling of same PV, but there is errors also there, like given some input of all thing. Sampling method is taking a large resistance, converter is there and it's load or not to take a maximum power from it. There is a small in some voltage sampling, but here we want to take a sample of given a switch, the one two pole one throw switch, this one like if one time here a, that time this one is a b. Here taken the voltage from here to here, this is taken as a sample of this voltage VOC, because of if there is an open circuit, it will connect it here. There is a resistance, or it is a large. This is the large resistance. You can measure the voltage of that one. It's like a open circuit voltage. That's one measure the VOC. Yeah, this is a VOC. Then after multiplication of K time, then it will become a VM. Then after you use the PI controller to take a VT same size as VM, and then use the PWM and given to the duty cycle to the converter. But here still you can't be operated this one in continuous, because of there's a sampling wise, this is the discontinuity in input side. At one time is a point to a to give the supply to the controller, then you need a large capacitor here to maintain the constant input voltage of a converter, and you need a sample and whole circuit also here to make a continuous of a discrete, because of if you take here, if you take a sample from the this, there is sampling like that, on time, off time, then on time, off time, like that, sampling voltage. Then how maintain the continuity? This is the discontinuous. Then how discontinuous value can't be tracked? There is a difficulty to track from a PI controller, because of this is the continuous. VT is the also this is the also discontinuity. This is also discontinuity. To track this one of a two signal is difficult in other, because of if you want to take this a VT, dry a VT, like if this is not a continuous, then how it will get, it really looks like there is the switch is off, then VT is taken like that. This is the VT signal. Then how can you track this to by PI controller? This is a difficult thing. PI controller track a reference value to the unknown reference value, like sense the voltage value. Then this is the error. Error can be minimized by using a PI controller. PI controller have no, this is the KP and KI. The gain of this one, they reduce the maximum power, like it should like be a constant, then it should be like that. Someone asking about something. It's a doubt which is VM is a VT at maximum power point and K should be less than 1. Yeah. Yes, VM is a VT at a maximum power point. Yeah. A VT is a VM, same as maximum point. K should be less than of this one. VM by VT. It's actually VM by VOC is the K. The VOC is greater than this the VT and VM also. That's why K always less than 1. Data sheet shows the VOC is 20 volt, Vmax 17 volt. What is the value of K? VM by VOC. This is the K. VT is different. VT is or at the time of moment voltages. Yeah, reference cell is the same. It will taken like a same value of open circuit voltage and peak power voltage. That's time that you can track the maximum power. If there are different thing, then you can't be track. If you different power, there is a different power, a lower power, but voltage rating is same for the both. And in current sampling method, the different power, but current short circuit current will be same for the same panels, lower power and high power, both main auxiliary you can say. If there is a different power, different voltage rating, then you can't be track a maximum power from them. They are just both are the VOC is same, but current rating is reduced. Yes. The PI control is reduced the steady state error because of this one. Here something here you can reduce, but for the variable quantity, if you use the PI controller, they are difficult to track the quantity. That's why they are used a capacitor as some holding circuit, hold circuit, sample and hold circuit. Sample and hold, it means a sampling. There is a sample, this is fine, but it will hold for the some time, like that. Then it will be useful. Because of this, so the changes in every time, because it will be depending on the VOC and depending on the sunlight, it will be changes. But it will just hold something like using a capacitor. You can reduce this one, hold in capacitor in analog system, capacitor there, but in digital system you can directly hold the same quantity for them. After that, it will be reduced for the same quantity. But in analog system or the filtering, there is a capacitor to filter the voltages. It will hold for some time. Then after it will take a sample, then hold for some. Then this is the approx continuous signal you can track. Same thing is here also. It will look like this one because of the capacitor. It will not continuously charging. That's why it would taken like a constant value for both and track this one by using a PI controller. This is a method to take a maximum power. For the power slope, you use the track of power. Where is the maximum power? Then you need to track a voltage and current both. There is a sense the both. Then after multiplication of this one is the power. Then track a power and voltage, compare of them, which one is greater, which one is the lower. Then what is the difference? dv by dt, like dp by dt and dv by dt. Changes of power and changes in voltage. Then after you can say where is the or waveform is going. Then use the duty cycle to step up or step down. I'll give some idea of this one. VOC, this is the power. This is a maximum power point. Same thing for the current Im, and this one the Vm. If we track this one voltage and current and make a power, then take a track a power and voltage to increase or decrease the duty cycle according to this. People, you know, P is equal to V into I. If you differentiate this one with respect to the voltage, then this will be two variables. First one, if you take a V, then second integration di by dv, then take a first one and second v respect to the v is 1. For P max, you know, for maximum power, maximum thing, anything, maximum value, the differentiation will be 0. Differentiation, first differentiation is 0. Then you can calculate di by dt here, di by dv plus I is equal to 0. dv is equal to minus of I into v, I by v. So what's happening here? It means at maximum power di by dv and I by v, it should be equal to 0. For maximum power, it will be greater than 0. It means left side here is somewhere. If it will be lesser than 0, then it will be here. If you goes here to here, you can say this is the voltage of increasing voltage. But current will be a decreasing in nature. That's why if di by dt will be calculated I by v, this thing, then you can find the left at the left side. This will be a less than 0. It means the whole thing is negative. And after this one, it will be a positive. Oh, sorry, this is the left side. This is the right side. You can calculate this thing from here, from this that equation. Equal to v into di by dv plus I. You can take this into di by dv. This will be a dp by dv minus of I divided by a v. Whole thing depending on the dp by dv. It will be a here you can say from here to here voltage will be increases but power also increasing at the left side, but at the right side voltage increases but power is reduces. You can say there is the both are increasing. It means both this will be a positive value. Then the whole thing is it may be positive or negative depending on the this value I into p. But I is reducing here, voltage is increasing, then the whole power thing is positive. That's why this value is positive in the at the left side. At the right side, you can say voltage increasing This will be increasing, but power will be decreasing. The dp it means the voltage difference between a new value to old value. The new value is lower than the old value. That means the negative. dp by dp is negative here. Then this will be negative. Then the di by db plus this will be also negative. The whole this one is negative, this negative, whole thing make a negative. Then this will be the left side, right side. It means if here is something, then you need to increase duty cycle or decrease duty cycle depending on the converter. If there is a boost converter like that, if you want to, you should decrease the duty cycle here. Then after here, if you go to here, then you need to increase duty cycle to make the maximum power point. Let's just start the questions for today. Which is the more accurate scaling reference cell method? A voltage scaling method or current scaling method? Yeah, current scaling method, because of the current is directly proportional to insulation. But voltage have some logarithmic. Yeah, power slope method too is the, okay, I will explain later in the question. This will be the directly proportional to the insulation. That's why current scaling method is accurate. For the voltage scaling reference cell method, find the values of a Vt into 100. Vt is terminal voltage of PV panel into 100 within the 2 decimal point for the specification given below and the given controller of the diagram. Please carefully see the value assumed ideal circuit and DC converter is operating in under continuous conduction mode. Into continuous conduction is mentioning, if there is no mentioning of a continuous conduction mode, then we will take the continuous conduction mode only. Still there is no mentioning directly discontinuous conduction. If I mention the discontinuous conduction, then we take it discontinuous and either take a continuous only. Output voltage is given. This voltage is 15 volt, and the PV open circuit voltage VOC is also given 32 volt. The voltage scaling ratio is 0.7 for the K1. The proportional controller gain is given 10. Converter is a buck boost converter. It means this is the buck boost converter. Then what is the input side voltage? This is the output voltage. You know about dBs divided by a 1 minus d for the buck boost converter output voltage. If output voltage is given, input voltage is not here given, then we want to calculate for first duty cycle, then after. Okay. Vm into K1 22.4. Yeah, approximately. Vm is equal to K1 into VOC. It will 0.7 into 32. 24. 4. You can say it about the maximum point. This will be same as the V in, maximum power point of V in of the converter. and output voltage given as 15 volt. Take these two and calculate the duty cycle or from PI TPS divided by the 1 minus T. Then value of D is equal to V naught divided by a Vs plus V naught. 15 15 0.4 is the duty cycle. Here is given a formula to how circuit for the duty cycle. We get the duty cycle. Duty cycle is 0.4. From here, you can say this is the Vm into K1 minus of Vt. You have to calculate Vt, this Vt. So Vt into K is equal to duty cycle D. Here is the carrier signal. Carrier signal is not affected in the magnitude duty cycle. It will make a magnitude of a duty cycle in a discrete. Like I think you have explained this one. Dude. Something is a reference. This is the duty cycle. And the sawtooth wave of triangular waves they were there to make this in the discrete, I can say digital signal, on off signal given to the, this is the carrier signal BC, reference signal PR or something, you can say duty cycle. Then you can find the duty cycle here. This will be a on when this is the maximum, off, like that to make a on off signal, like a discrete signal, to make a continuous to discrete given to the your converter. That's why the reference signal is required, but it is the same as the duty cycle D. Then Vm we calculated. Vm is a 22.4. Vm into K1. K1 is also given. Vm into K1. Okay, VOC is given. Okay. Then you can say both those is 22.4. I think this is the VOC, not VM. VOC into K1 is equal to VM. 4 minus VT. VT you have to calculate this one. K is given 10. Duty cycle 0.4. 22.4 minus of VT is equal to 0.04. Now what is the VT? VT is 22.4 minus 0.04. It will be 22.36. If you multiplication of 100 VT into 100 of this one, it will be 2236 volt. For this question, look, given the VT into 100, what is the value of VT into 100? Which one VT? This one VT. You want to find this one, or a terminal voltage of this one. You can find this voltage. Now to find, you can track this controller design and simple use the multiplication. It's given in the question. VT into 100, asking about the question VT into 100, not in practical cases. This is the questions value, not practical value. This question is given okay, VT into 100 value of VT into 100. What is this one? That's why multiplication of the 100. For the same question, find the error as K1 into VOC minus VT into 100. Same thing I think we'll calculate it already. K1 into VOC minus VT into 100. So 22 point something, 2.4 minus this only 22.36. Oh, I think same question. 4, 0.04. From the specification of question 2, find the duty cycle D within 3 decimal range from 0 to 1. Duty cycle we have calculated 0.4. Something asking something. VM you calculated as 22.4. Then why we took VM into this is I think why mistakenly printed VM. This is not VM. This is VOC. VOC multiplication of K1 is VM. This is the not a VM. This is the VOC into KM. This whole value is VM. That's why I'm putting directly 22.4. After VM, I'm not multiplied a K1 again. This is VOC. This is the VM minus VT. This is the misprint of this one. Don't worry. Duty cycle for a 3 decimal. Within the 3 decimal is asking within the 3 decimal place. Then use the duty cycle is V output divided by a V input plus V output. The V output is 15 volt and 15 divided by 15 plus 22.4 0.401. If you take a more precise duty cycle, then you will get the more accurate maximum power point track point in the algorithm. Sorry, if you take a lower value like a single decimal value, then there is a more oscillation at maximum power point. Okay, I will explain this one later. If you take maximum power, the maximum power here, suppose not sorry, this is the maximum power. And if you take a more accurate duty cycle, more decimal places, then you have a oscillation of this one like that only. If you take a lower value like a 0.4, yeah, 0.43 like that only, 1 or 2 pairs, I mean, this one is the more oscillation. They didn't like that to oscillate like that at a maximum power point. It will go below this one. Then after you sense the next sample of the voltage and power, then it will return to back. Then after you go to here, it will be oscillated. But if you give the more accurate value like 0.4321 like that, then this will be oscillate at the middle point only. This one like that. No, instability you can't say directly it will give instability, but depending on the converter, converter have deflection is there in current, voltages also in input side, but there is a large capacitor to neglect the ripple in input side. That's why this is not more effective. But if you, this is oscillator is more, that right, that's one can be affected to the your microcontroller or converter because of there are switches and there is ringing occurring in switches. If you try this one, at high level, this ringing is there, then it will be switches will be heated. That's the problem. Then use this one as accuracy as possible. Don't take only the words. Don't be take a single digit, single decimal. What do you take this one? At least two or three. You can observe this one in our simulation. If you do a simulation of a buck converter, push converter, buck push converter, then you can see it. So the simple thing. That's why I think this question is asking about the three decimal places because this is a requirement of it. So that one. Next question is related to the gate driver circuit. Gate driver, it means MOSFET gate driver or IGBT in the switches. At the place of switches, use the IGBT and MOSFET, but in converter side, there is a high frequency rating. I think IGBT you can use as a maximum of 20 kilohertz is enough for IGBT or high power 20 kilohertz. More than 20 kilohertz you can be after some of the IGBT is there, but it is mostly operating in maximum 10 to 20 kilohertz used. But in your converter, DC-DC converter, use the 50 kilohertz, 100 kilohertz, and more than 100 kilohertz also. There is a converter you used because if you want to reduce the size of the converter, a DC-DC converter. If you reduce the size of converter, then you can say the cost and efficient also. But there is another drawback of the switching losses. If you increase the switching frequency, then there is a switching losses. The gate driver is an important thing. So the isolated, not isolated gate driver is there in the market and they are used in laboratory. But a simple diagram to how to turn off the gate of the MOSFET, IGBT. They given is the gate voltage, there is the output voltage. Then is asking like there is no means inverted point. They are just same as the voltage given, the same pulse as the output side. But sometimes there is a need of the inverted voltage also. And you know about the a leg of inverter. There are just two switches there. This will be on off in complementary method. This will if this was the on, this will be off, and this will be off, then this will be on. 1010 like that. They needed up this requirement of this. So that time you need to that type of MOSFET driver which will give to the both it will you negative of the one signal. That's why you're asking so how the same voltage. Why which one is the same voltage? There's IGBT. There is a NPNP type NPN type. It is used like in it is used like a switch. IGBT, this IGBT is used in like a switch in saturation mode. When voltage is 1, gate voltage is 1 high, suppose this is the high, then what happened? Current is flowing here and this voltage is on to this one, positive voltage here, negative voltage here apply, and PN junction diode will be forward biased. This is the you can VE VB. If this is greater than 0.7 volt, then this will be a on. If this is the on, then what happened? If this is the on, the IGBT is on, it means this will be a short circuited. This is circuited ground, ground is here, output voltage is 0. It means it's given to the 1, output is 0. If it is 0, the output is 1. Complementary. This driver is in complementary method. And what's about the B option? This you can say this is not correct for this question. Now this is the high, current is flowing here. If this voltage is greater than the VBE, that means this will be high. If this will be high, then this terminal is directly connected to the ground through this one. If this is the ground, it means this is the PNP transistor. In PNP transistor, this will be the forward bias, and this will be an active mode. Switch mode. This will be on, and current is flowing like that. Current is flowing like that is the e- register is there, then you could get the voltage of 1, high voltage here. If there is no resistor, then this will be ground, both are short circuited, and the 0 voltage given. But here the output is 1. You given the input 1, output is 1, you can say this is the matched to the question. Next here, if you given 1 power supply, then what happens? This will be high, this will be high, then this terminal is connected to the ground, and this means a 0. If there is the 0 voltage, then there should be a PNP transistor. PNP transistor, you know, if given the 0 voltage and base, then this will be a forward bias, and this will be a, this is also greater than the 0 because of this diode. This will also forward bias and goes to the saturation region and attach a switch. It means this is the short circuit working like that. This will be 1. If this is a 1, there is just some voltages. No, there is some voltages. This voltage applied to the VBE. It means there are some voltages here. There is a high voltages, then this is the NPN transistor, and this is the PNP transistor. The NPN transistor, if a base voltage is high, then this will be a forward bias, it will working. And this is the working, that means this will be short circuited, the output voltage is 0. Here high, then this will be 0. This is the connector here, and this will be the 0 voltage because of the, it will connect it to the ground. If given to the 1, it will be 0. Okay, if you give it to the 0, then what happens? This will be on, off. If this is the off, then this voltage is, no current is flowing, the this voltage is same voltage appears to the base of the PNP transistor. Then there is a base voltage is there high to the this one, and this will be a 0, no turn off, and this will be 0, this will 0, that means PNP transistor will turn on, and this voltage appear directly in output side, and this output will be high. It means it will go to 0, this will be a 1, we given to 1, this will be a 0. This will be a complementary switches. That's why for this question, B option is correct. Next is the for the IV characteristics of PV panel. Find the terminal voltage in volt at which maximum power point happens. Okay, it is asking about the voltage VM. Current equation is given, I is equal to minus 0.21 V square plus 24.3. You know about the P V into I, then multiply of this one. If you want to integrate this one to dP by dV, then we will get this one Vi plus V into di by dV. Same thing, you know about P max, this will be 0, then di by dV is equal to minus I by V. So okay, then what happened? Differentiate this one at once, and we get the di by dV. This will be a minus 0.2 V plus 0, will be a constant. Di by dV is here, then it will be equal to minus I by V for maximum power point is equal to minus 0.2 V, then minus will be cancel out, then I is equal to 0.2 v square. I equation is here, minus 0.1 v square plus 24.3 is equal to 0.2 into v square. Then we take a v square at here, that it will be a 0.3. V square is equal to 24.3. Then v square is equal to 81 divided by this one, and v is equal to 9 volt. Then what is the power? 5.19. What is the 5.19? Just explain, please. V is 9, correct? Okay, you know about the IB, di by dB. This is the at a P power, maximum power. I equation is given di by dB, then calculate dy by dB from this equation, equation number first here. Then this is 0.2b, and you know di by dB same as the I by V for a maximum power. Then put the value of I, same thing here, and calculate the V here. Calculate V is equal to 9 volt. Then what is the power? P. The first calculate I. What is the I in this equation? Because of this equation given from PV panel specification, V square plus 24.3. Then I is equal to this is point, V is equal to 9. 9 square is 81. Then it will be 8.1. 24.3 minus 8.1. It will be 16.3. 16.2. Yeah, so 16.2. Then P is equal to V into I. 9 into 16.2. 148 145.8 watts. Okay, fine. For the IV characteristic, V panel find the terminal voltage. Is asking about terminal voltage only. At the which maximum power point will be high pair. Terminal voltage is 9 volt. At 9 volt, you get the maximum power. What is the maximum power? It will be 145.8 watt. Yeah. In questions, next question is asking about the maximum power. To the watt. It will be same. I calculated. For the question 6, same thing. If V is equal to 7 volt, then select one of the following option. dP by dP less than, greater than, or equal to 0. You calculated Vt. V is equal to 9 volt. This will be a below to this left side of this one for the maximum point. This will be a 9 volt. Here something is 7 volt. If a V is equal to 7 volt, then what is I? I is equal to minus 0.1 into 7 square is 49 plus 24.3. Then I is 19.4 ampere. And what is the power? Power is equal to 135.8. Now what is the dP by dV? dP by dV means simple, delta P divided by delta V. Same thing like a P2 minus P1 divided by a V2 minus V1. P2 already calculated, 145.8 minus 135.8 divided by a 9 minus 7. This will be a positive, I think. 5 greater than 0. Yeah, first option. Same thing if voltage is more than 9 volt, it means 14 volt. Then take same thing and calculate here P2 minus P1. I think written here is wrong. But if both cases negative negative will common cancel out, final equation is positive only. So P2 is here, so we can interchange. Same thing apply here, it will be a negative I think for 17 volt. For the sixth question, previous question, for the power slope method 2 control as shown in the lectures, select the values for which the output of a comparator after absolute value calculation is positive. Okay, the power slope method same for the calculating a maximum power. Take a controller converter, for taking a maximum power from a solar. The load is also an important thing. The current rating, if suppose if your converter is given a maximum duty cycle, at that maximum duty cycle there is no current flowing some amount, that one is the IM, then you can't be get the maximum power. Then load is also important thing, that's why there is the variable load is given like that. In the power slope method you need the two, both power current and voltage, then after you take a power multiplication of both. Then how to calculate the sense the voltage and current. For current sensing, simple, we use the current sensor here and take a current IT. For a voltage sensing, you use a circuit, a switch is given like in pulses to take a open circuit voltage from this one, a VT you can say. This is the something resistance R, which one is the very large to the or not, which means this will be an open circuit. When switch is on, then you can measure the voltage of this one. Then from this one, we take a VT voltage, then multiply by both to make a power, and this will be a power circuit. After that, then what happened? Current and voltage will be in pulses, both are in pulses. This is also pulses, voltage, and switch is on, there is a voltage like that. Power is same and voltage and current multiplication, then power is also in pulses. then it will be a somewhere like that. Current is also some like that only. You know how to get this one voltage and current. See, if the switch is on, if the switch is not on, it means zero. Open circuit, then current is flowing continuously here from here, okay, to the load. If switch is on, then this circuit is completed. Then some amount of current is flowing here also with this one, like that. Then what is the overall voltage from here? Input side is looks like a current, looks like this one. This is the average voltage or average current which will flowing to the output to the converter. But if the switch is on, then this pulses current is also there. Same thing in voltages. Voltage measure is continuously. It will be some voltages, but in when switch is on, then there is some pulses. Then this is the pulses voltages also there. Then how get the same voltages? Pulses voltage. Want to redo? Want to neglect this one? Reduce the uh, subtract the output voltage of the DC voltage of this one. DC voltage, that means you can say average of this one. We have required of positive and negative like that to make a toggle or to make switches like that. If you goes to the downside, it is negative, then pulsar is on to get feedback this one. That's why you need to subtract the average value of this one. I can use the remove the DC voltage. Now I use a block which will remove the DC voltage. You know the remove the AC the DC average value of this one. Use a DC voltage block which will remove the average DC value. You know how can you know how you do the DC value and average value are same? Just I want to explain. Just don't confuse between them. Suppose Fourier analysis. I think all of you know about the Fourier. If suppose there is some signal like that, then what happen? Any signal. Suppose this is the voltage current time. And Fourier save any signal rather than the sinusoidal AC signal, DC signal. It contains a AC quantity which is the harmonics. It, it means this is there is a naught average value of that signal, this signal. After that there is a sine and cosine. Then this one sine and cosine value is known as the as a AC signal, a harmonic signal. And there is a average. After that, all quantity is considered in the AC, a variable quantity, and harmonics. That's why at every signal which is not a pure DC, then there is a DC value, and after that there is a harmonics containing. That's why I am ask this one. This is the not pure DC signal, not pure AC signal. That's why there is a some DC value here. Average value is known as the DC value. That's why I want to remove this one. I will take a only AC signal from this one. I only pulses of this one to compare the previous one and new one. If you remove the DC value, then what happen? You get a sample like that. This one will be a like that only, a positive or negative symbol. Same thing here also. Power and voltage. If you suppose, if you, this is the very less amount of value, you can say this is the very less value, because of the this one value is, when resistance is very high, because you can't be lost the all maximum power at that resistance only, then you need some pulses which one not more effective to the whole converter for maximum power. Suppose if you take a lower resistance and higher current is flowing here, then what happens? More of the losses is there only of your PV panel. Then how you get the maximum power? That's why there is a higher value. That is means there is a very low amount of current. Which one you can't be measurable? A very, you can say there is the very low value. Then how can you take this one? I take a action of taking this value. Then you need to amplify this one to higher value, higher pulses. You need only pulses. Yeah. That's why you use the amplifier, which one is a zero, after zero crossing the detector. Which one? If this is the positive value, then there is the given a VCC value, which one VCC may be 15 volt, 5 volt, like that. Then it will given same signal in higher value. This is the VCC, this is the minus VCC. It means same thing. If this there is a positive value, then given output is the plus VCC. If there is a negative value, then output is the minus VCC. Like that. Same thing here. After that, you want to add more signal. Then what happen? Voltage. This will be a current. Voltage current waveform is like that. Then power. A sampling of voltage and power, and voltage and current is taken. Then if voltage and current taken, voltage current multiplication is the power. Then there before it will be maybe before of this one, before the maximum power, or sometime it will be maybe a maximum power, or both condition is possible. And this is the P max. If the current is flowing like that, on off, at that current power is this one, at that current power is this one. No? With this current power is this one, that current power is this one. Same thing in voltage side also. At that voltage this is power, is this voltage this is power. Same thing if possible cases, if second possible cases, yeah, right side the maximum power, then what is the power, what is the voltage variation. Okay, suppose here is the somewhere, then we take a power P and voltage V here. Power P, this is the P, this is the V is taken. Suppose here is there, voltage is lower voltage, hey, this voltage, after the switch is on, this voltage given pulses. Then we can see at this point, here voltage and power both are increasing. Voltage is increasing and power also increasing, and both are in same, you can say both are in same phase. If both are same phase here, then if you want to add this one, not subtracting, add, then what happen? Both signal is add up and given the larger signal. Make a larger signal like that. Suppose if this is the VM point, maximum power point. Suppose the right side, if you go to the right side, then what happen here? Take a power, maximum power graph. This one is the maximum power graph. You can say, see this one. Suppose this point is this one, same point is this one. At that point, voltage, some voltage. After that, voltage here is increasing. Here, you can say this is the this point. The voltage is increasing. Suppose this one. The voltage is increasing. Then what happen here? But the voltage increasing, but at this point, power is decreasing. It means delta P is negative, voltage is positive. Both are in opposite phase. Both are opposite phase. We can take in that both are same signal. Then what is the output voltage? Output of that signal, addition of this one is be 0. Then same thing passing through the absolute value. If passing through the absolute value, that it may be a positive or that it may be a negative signal. If both signal add up larger value, and the absolute value is absolute, it means negative point is clapping to the positive curve. Then there is some this one like that. Then average of this one is Vt, threshold voltage which is given to the making a PWM. Then he's asking this one, and after absolute value, this will be a left point, this will be right. At the left point there is some voltage, at right point this will be 0 voltage. After this will be a comparative signal. This will be a compare to the phasor voltage, terminal voltage you can say. If this is the voltage is more than this one, then the output will be positive. Same thing, multiplication of gain. After that you can say using a PWM. PWM directly can be used because of this is the pulses, it will come into the pulses. Here in this slope method, after the absolute value, here the signal positive or 0, left is positive, right is positive, but left is absolute value connected to the negative terminal, and the right second one is a threshold voltage is the positive terminal. If this one is the higher value, then this is passing through the output. If this is the output signal, then this is the negative, VCC is output. You can say this is the opposite of this one, 0 to 1 like that. After this, there is some filter used. Filter is using to maintain the constant value, not the duty cycle, to compare to the PWM like that. This is the DC, same thing, LC RC filter like that, to make a constant to remove the pulses in a constant value to track this one, this duty cycle. If there is a positive, both are same. Okay. If there is some positive value, negative, the duty cycle is decreasing for the boost converter. Duty cycle is decreasing. If you can say this thing is used for different buck boost converter. If you need to increase the duty cycle, then same thing you use the positive terminal to that one is a negative terminal. After that you use the gain filter, then this will be duty cycle, it will be increasing because of the there is a lower value to the BT. Sorry. For the buck boost, you can calculate from this signal only. Any converter, voltage and current. What is the duty cycle? You know, previously I give some idea for the boost converter. Here to here is working. For the boost converter, this is the duty cycle is equal to 0. This is the duty cycle is equal to 1. Okay, but your maximum point is here somewhere. For the this is for the boost converter I explain. For the boost, this is duty cycle 0. This is duty cycle 1. Suppose you are here at that point. You want to reach here. At that point, it means this load line is looks like this one. But you want to go here. It means you want what happened? Is a duty cycle something between 0 to 1, but greater than 1. This duty cycle is greater than 0. This is not a 0. It's 0 here something. Suppose here something is equal to 0. Then what happened? You want to come that point, then this will be shifted to down. Then how it will shift to down? It will be shifted to down when you decrease the duty cycle more. You decrease it, then this load line is shifted down. Then somewhere after some time it will be a exit that point is tracking in boost converter. If suppose if you are here but you want same thing, if you are here, okay, somewhere something duty cycle this will not possible because of if you take a duty cycle 0 here, then you should be here between them only. Suppose duty cycle is greater than 0 something, okay, but is not a P max, then what happen? If you are here after that right point here, right side of the P max for the boost converter, you want to go to the top or go to the P max here this line, then what happen? Duty cycle simply increasing in this condition. In that phenomena, you can take action how increasing and decreasing for buck converter, boost converter. Okay, I think this is the so confusion. Okay, well, I just explained for the buck converter, same thing. This voltage, this is a current. Oof. P max line for the buck converter. you know duty cycle from 0 to 1. For a 0 duty cycle, it will be 0, d is equal to 0 here. Suppose somewhere is d is equal to 1. This is the operating area for buck converter. It's same thing, 0 to 1, it will be looks like that. If you are here, somewhere 1, that means this is the load line, looks like that. But you want to go here, that you want to shift the duty cycle. It means you do have to decrease the duty cycle here. I think same thing for all these converter. It's the same thing you have want to say. Same phenomena. If you left side, then you have to decrease duty cycle. If you right side, then you have to increase the duty cycle to track the maximum point. Will be possible when you want to this will go to the negative absolute value to the negative point. If you give to the positive point, then what happen? Duty cycle will be increasing if you power is decreasing. That's why. And then the question is asking about the ah, select the values for which the output of the comparator after absolute value calculation is positive. Then what happens? P max, you know, V max, we have calculated in previous question is 9 volt. Next iteration, if less than this one, 9 volt, then what happen? How happen? This absolute value will be negative. But we want to this one. Then what happen? You should take the maximum V voltage greater than the V max for next iteration. It means increasing voltage. Okay, let's 1 second. I explain again. Asking about select the values for which the output comparator after absolute value calculation is positive. It means this one. You can say this will be a negative value. This will be the positive value. Then when you get the this value, positive value of a comparator, this is the comparator. Which one compared to the this voltage to this voltage? Threshold voltage is something. This one. If it will be greater than this one, then you will get the negative voltage. If this one is lower than this one, then you get the positive voltage. When you get the positive voltage, when you get zero voltage of the absolute value, then when it will be a zero value of absolute value, it means both are in opposite phase, and both are in opposite phase, then which value is right side of the P max. Here here both are in opposite phase in right side of the P max. Then we'll get the negative value, and outward phase both are 0 and 0, then comparator value will be positive. The duty cycle will be increases at that time. That it means you choose the max voltage is greater than the P max, sorry, V max. The I have calculated in previous question, in question number 6. uh, V max is the 9 volt at a maximum point. You know Vm, I have calculated like that, get the 9 volt. Then you should take the V more than the 9 volt. The Vm, not a max, you can say Vm more than the Vm. Then what is the value when more than the Vm is 12 volts. Okay, at the maximum point, di by dt is equal to, okay, same thing, di by dv plus I by v is equal to 0. So at the maximum point, that will be a negative of this one. Sorry. A reference cell voltage scaling method is used to track a maximum power point for a solar panel. The open circuit voltage is 46.3 volt or 43.6 volt. Then the voltage at a maximum power point is approximately. Eh? VM, you know about this one will be K into VOC. K is not mentioning, but is approximately average default value is 0.7 volt. VOC is 43.6. I think 30 point something. Uh, K is normally it's zero point 0.7 volt or maximum power point. You can say and take on data sheet all of things, and it will approximately this one. It will not you can't be say that this is the exactly for all final, but it will be approximately 0.7 times of the VOC. That's why. So, oh, the maximum duty ratio of this following gate driver. You can say this is the isolated gate driver. There is a two drivers, isolated gate driver and non-isolated gate driver. Then why is new need of the isolation and not isolation? Non-isolation. In isolation, there is a extra circuit. Transformer is here. In non-isolation, there is a no transformer. Direct signal you can give to the microcontroller to the gate driver of the gate to the MOSFET. Okay, fine. Okay, I want to just explain in practical cases at that time what is the need of this one in practical cases. Then after I give the answer of this one. Suppose you want to make a buck converter. Okay, fine. Want to make a buck converter, then what is the circuit of this one? A DC voltage. They use the MOSFET. I have written like it three terminals. First terminal is always the gate. How if you see this one. Second is the drain. Third one is the source. In a data sheet, if you take, if you want to take a MOSFET and give the part number of in our Google search and search them. Then if this is the always first gate, this is the drain, this is the source terminal. Then after there is a diode. Diode you can simply connect it, no problem, because diode have a uncontrolled device. Sorry. Just give idea how to make a buck converter in your laboratory and how you can do drive. You can take an inductor and you can take a capacitor, resistor according to the data, according to the calculation of buck converter. Simple. BS. I'm not going to that thing. I just explained how to give a gate signal to the MOSFET. Okay, fine. Yeah, in simulation, you just directly connected the pulse generator and given to the mask microcontroller, MOSFET gate terminal, and it will be turned on and it will be working. But what is in the practical cases? Can't we give this one? VGS, gate to source voltage. It will be a requirement of any MOSFET. It will be depending on the MOSFET high power. If you go to the high power, it will be a 5 volt to 30 volt, or sometimes some microcontroller have needed of the 12 volt, 12 to 30 volt, or something like that. If you take a data sheet of my MOSFET, then you can read the for which VGS you can turn on successfully of a MOSFET. So 5 is the minimum value, but you can't be turned on this. There is a very large resistance in our MOSFET part. That's why in normal cases we are taking a 15 volt. Yeah. There's a 15 volt supply pulses, which one you can give to the gate to source of the MOSFET to turn on the MOSFET. Okay, fine. Suppose there is a microcontroller. Okay, I'm not going to go to inside. There's a two signal. The positive, which one is the gate pulses generated from the microcontroller. Second is the ground. Then what is the in time we can measure this one. This voltage is maximum of 3.3 volt or 5 volt only. A microcontroller can generate pulses of 3.3 volt or 5 volt only. It can't be generated 15 volt of pulses. Then how can you generate the 15 volt? Then you need a driver circuit. Then you need a driver circuit. Same thing, this type of driver. This is the driver circuit to turn on the MOSFET. Here is the pulses given from the microcontroller. Here is the MOSFET, and this is the all circuit to turn on the MOSFET. And how you can turn on this one? Fine. Suppose if you use any, there is suppose 8 pins ICs there. You can connect. You can connect this one with directly or through a resistor to limit the current in a short circuit cases. And this ground will be terminal to the ground terminal. Okay, fine. These are generated the pulses. Okay, this is the ground. Suppose last one. There is a requirement of voltage supply. How much voltage supply you gives to this that driver? Same voltage supply is given to the gate signal output of the pulses. Same thing. This is the VCC. VCC is it is in your hand. How much VCC you want to supply or you want to get give to the gate gate voltage of the MOSFET. If you want this is the 15 volt, then what happens? If you give it this one, the same 15 voltage occurs here at the input of the MOSFET, and MOSFET will be turned on. If you will give this one a 20 volt, the same pulses will be a 20 volt of this one. Here is a 5 volt only, this is the 20 volt. It depending on the how much power supply you want to give. Generally, we give the 15 volt, then 15 volt supply is connected here, VCC. This is the ground. Okay, pulses is occurring here, W. Then what happened? You want to connect this one, this gate to that gate. A gate to source. Source should be a ground because we need a reverse terminal, reverse current to pass the complete the circuit. Current will flow like that to turn on the gate signal. After this, we like that. Just a simple circuit. Then there is a problem of isolation. Suppose if you want to give same supply here, same ground to this one ground, sometimes it will be same because of the this both are the uh, power supply. Then you can give this power supply and introduction of this power supply to this one. Then this is the positive terminal, this is the ground terminal. This ground. Then what happened here? Yeah, you can say this same supply is given to this one. Oh, sorry. Same supply given to this one. This ground, and this ground both are same. There is no isolation between them. Okay. Then what happened? If you given to the pulses positive connected to here to the turn on the gate. Okay. Source what happens? Source connected to the ground, and same ground is connected to the here because of the, if you want to there is no isolation between them in this one in this circuit. The whole ground is same. Then what happened? This ground is be this ground from here, and we can see this ground, and this will be a source circuit. When switch is on, then this will be a source circuit to the source in buck converter. In buck converter, you can't be gives the non-isolated supply to the grid driver, or a gate driver, non-isolated gate driver can't be used because of same thing. This is the floating switch. This is the floating switch. It means you need to isolate supply, isolate the driver supply and driver. That's why there is a need of the isolated driver. This is transformer to isolate the input side and output side of the driver. Next thing comes to the questions. What is the maximum duty cycle is flowing through the gate driver? Maximum duty cycle. Microcontroller can be generated duty cycle from 0 to 1. Then this driver can be handle 0 to 1 duty cycle, and if it will be not handle, then why it not handle? You can see there is a transformer is here. There is a VCC is a voltage supply of DC voltage supply. A DC voltage supply is connected to the transformer through a switch. This will be a switch. If this is the on pulsar, then this will be on. The current will flow like that. This power supply you can say we connect here like that. This is the same thing. As the switch is on, then this power supply VCC is connected to the private terminal of the transformer. Okay, and this will be isolation 1 time to 1 something. This will be 15 volt. So it also 15 volt. Go to the output. Dot is here. If dot is positive, first time connected the positive, this dot will be turned on. Positive terminal, this will also turn on because of this that voltage. So the zero voltage, ground voltage, and this is the resistor to limit the current, and then this will be a 15 volt supply occurs here, VGS, and this will be a turn on like that. What happens? Zero. This will be a turn of zero. Then at that moment, what happened? Transformer is supplied a voltage, some voltage like VCC on time. Then any transformer or converter is working based on the flux balance. Transformer is not working in is DC side because of this one only. There is a no flux balance. There is an increasing flux. There is a no variable. In AC time, this will be positive and negative voltage. That's why in positive time flux will be charged. Sorry, core of transformer will be charged. After the second half, the core transformer will be release the energy. You can say this is the discharge. Flux will be reduces. Then the whole time flux will be balance, charging and discharging plus. Same thing will be happen here also. If there is not happen, then that transformer will not work in DC mode. Then there is some negative power is required. Yeah, there is a path. There is no there is a requirement of a path to discharge the magnetizing energy of transformer. That's why there is a snubber circuit is used, a resistor and a diode. After second half, the switch is zero. Then what happen? This will be a positive, this will be a negative because of the this current will be flowing like that. Then whole energy is spread through the resistor. Then what happened? This will be positive, this will be also positive, this will be negative. Positive connected here, negative here, this will be reverse bias. Then this will be also reverse bias because of this one only. That will be not working at that time. This is the NPN transistor, N, sorry, PNP transistor. Then what happened? If there is a zero voltage, this will turn on. The turn on, the gate charge will be dissipated. The whole energy charge to this one. For this will only for the fast discharging, a fast turn off. If you not use this one, then there is also okay. There is no problem. This is used for the fast turn off of the diode through this. This is zero. This is zero. This will be forward. This will be, that's why the zero voltage occurs at the terminal of this one. And diode will be MOSFET will be turn off, zero. Then what happened here? This voltage current is flowing like that. In the on time current will be charged, magnetizing current of transformer. Second half, this there will be discharging through the resistor. There will be a discharge through the resistor. Then the value is positive, negative. Current is flowing through the resistor. There is a voltage drop. Same voltage drop occurring at the terminal of the MOSFET. In negative side, this will be like that only. It may be because of this is the V by R minus e power minus T by tau. Because of RL circuit, it will be purely RL circuit to the diode. Then there is a current I, it looks like that in discharging mode. The voltage of this one will be like that. Sometimes if you fully discharged, then that's continuous. If it goes to the zero also, and this will be happen. Then what is the maximum duty cycle? How can find this one? Maximum voltage you can apply in positive direction is VCC, and the maximum voltage will be here. It may be VCC. If the maximum voltage can be applied the reverse wise because of at the time of the zero short circuit open circuit of the this gate driver, zero supply from the gate, then what happened? The whole energy, whole that current is flowing through this resistor, and maximum supply will be a minus of VCC only. Because that one voltage appears to it. It will be not a more than the 1 volt, more than the VCC. Then you know about the volt second balance equation. On time Vm dt time plus off time Vm 1 minus d t time. Average of this one will be 0. Average voltage 0, it means charging and discharging of the flux will be same. Charge and discharge, it's balance. That's why known as volt second balance equation. At Vm time maximum on time, this will be VCC into d, tt cancel out. In this in off time, VCC will be a Vm will be a minus VCC maximum duty. For the maximum duty cycle, you can say is the maximum with the VCC minus VCC into 1 minus d is equal to 0. Dm you can say VCC Dm minus VCC plus Dm into VCC is equal to 0 to dm into vcc minus vcc is equal to 0. Maximum duty cycle is equal to vcc divided by up 2 vcc is equal to 0.5. In this condition, you can't be apply a more than the zero point 0.5 duty cycle. Why? If you charge in that time, zero point 0.5 is the same time. At the same time is charge any inductor, then it will be at least take a time to discharge of same power for anyone. That's why it will take a maximum duty cycle is 0.5 only. The transistor Q1 in question is used, same thing, this Q1 used to fast turn off. If you can't use, then there is no problem. MOSFET will be turn off, turn on, but there is some delay. That's why is a turn off process is step up. When a BJT is used as a switch in buck converter and operate with cutoff region during the turn off and saturation region during the turn on, linear region during turn off and the saturation region in turn on, cutoff region during turn off and linear region. Cutoff region, a cutoff and saturation. The cutoff when switch is off, when switch is on, then it will use the saturation. In saturation region, you know the voltage and current is going to the linear and must BJT. That's why it is used in saturation region. After saturation region, there is some voltage like that. After suppose 7 point more than 7.5, 7.7 volt of BCC, BC, then there is a saturation. There is some active region where is the one diode will be in reverse bias, and both are the forward bias. This is saturation region. There is a linear graph of voltage and current. That's why it is used in saturation region to use the switches. Okay, everyone. I want to stop today for today here. If you have any doubts, you can ask. Okay. Thank you. Thanks to all. Good night. Yeah, there is some remaining paper. Okay, I will upload it. Okay. Thank you.